And at the heart of that idea is forces. In physics, we represent forces as vectors which have both magnitude and direction.
With both direction and magnitude. Oh yeah!
Okay, so usually a few different forces will act on an object, and we can represent those with what we call a free body diagram. So first, for an object in motion, let's say a box on some surface, you would assume that gravity would be holding it down, and then the force of the surface would then be holding it up. So then those two arrows are equal in distance to each other. But if it's in motion, maybe someone's exerting a force on it that's going towards the right. And then maybe there's just a little bit of drag on it coming back. For an object in equilibrium, it means that the arrows are going to be equal on all sides. So we can assume the same thing, the gravity and the surface pushing back up, but also we would assume that the force going forward and then maybe the drag would be equivalent, and then of course gravity and the surface.
Now on to Newton's laws of motion. According to Newton's first law of motion, objects at rest stay at rest, and objects in motion stay in motion unless acted upon by an unbalanced force. And now Newton's second law states that force is equal to mass times acceleration. Acceleration is the change in velocity.
For example, this individual was in motion, very evidently, until he was not.
For an object in a state of equilibrium, the net force is equal to 0 because the net force is equal to the mass times the acceleration, which is 0 in this case. Additionally, the sum of the forces in the x direction have to be balanced and also equal to 0, as well as the forces in the y direction.
Alright, so a moment is basically the turning effect around an axis or a pivot. So for example, we have a wrench tightening around a bolt, and so that turning motion is going to be measured by the force and the distance. So this is important because if there's no distance, so if the force has no turning effect on it, and it stays fixed in the position it's in, there's not going to be a moment. So it requires a change in the distance and an applied force. And the force is also always perpendicular to the axis.
So we're going to be doing an example about solving a very, very simple mechanics problem. Our example is a mass is resting on a table. You and your friend are pushing on opposite ends of the mass. The mass is in equilibrium. This is a key part. What is the force you are applying? What is the force the table is applying? The mass here given is 14 kilograms, and gravity we're rounding up to 10 meters per second. So we're given this diagram of the forces that are currently happening in this problem. So step one is always to create a free body diagram. In a free body diagram, we just want to simplify it as much as possible. So this mass we can turn to a point. We see that there's F1 acting in this direction. F2, which is opposing it. We know there's gravity acting downwards. And normal force from the table acting upwards. So from here, we can set up our system of equations. Using Newton's laws, we know that the sum, when in equilibrium, we know that the sum of forces in x must be equal to 0, and the sum of forces in y as well. So we can set up a matrix to solve this equation. In this case, our x is going to be our forces in x and y. And our A is going to be our identity matrix. So from our free body diagram, we know that our f of x is equal to f2, because it's in the positive direction, minus f1. Similarly, our f of y is going to be ft minus fg, because this is in the positive direction, this is in the negative direction. We can then put that back into our equation. So now we have our setup of this equation. There's a couple ways we can solve this, but just to practice, we are going to use an inverse to find our x vector. So we know that x is equal to the inverse of a times 0. In this case, because A is our identity matrix, the inverse of the identity matrix is just the identity matrix. So it's going to be rewritten times 0. However, anything times the 0 matrix is 0. So we get this. So rewriting this, we know that f2 minus f1 is equal to 0. This is just our x vector, 0 vector. Then solving this, very simple. f2 minus f1 is 0. f2 is equal to f1. Just a simple equation, and then f2 minus f2 is equal to 0. And we can solve that for f2 is equal to fg. So this is a little bit more complicated than it needs to be, but this is just to kind of go through the motions. And now that you have your systems or your solutions, you can then plug the numbers back in and get the numerical values. But it's always good practice to solve everything using variables first, and then plug the numbers in at the end to get the most accurate answer. But yeah, that's how you begin to solve a simple system of equations for a mechanics problem. So our second example is a massive balance between two strings. What is the tension in each string? So this diagram is given where this is our x direction and y direction. We see our mass is balanced between two strings. This is string 1 and string 2, each with a tension, so T1 and T2. We also know on this mass, gravity is acting downwards. We have force of gravity. And from what's given in the problem, we know that the length of each string is identical, and it's 2√2 meters. The mass is 10 kilograms. Gravity is rounded to be acting at 10 meters per second. And the angle formed here is 45 degrees. So using all that information, we'll do our first step, which is always a free body diagram. So to simplify this as much as possible, our mass becomes a point-like mass. We see T1 and T2 are acting at an angle on the mass. So we have T1, T2, and we see that gravity is acting downwards. Now from here, we need to figure out what that angle is. Using geometry, we can see that the angle here is identical to this angle. So this angle would be our theta. That's given as 45 degrees. From here is where we can begin to solve a system of equations. So now, using Newton's laws that the sum of forces in x and the sum of forces in y must be equal to 0 when we're in equilibrium. That's key. We can create these equations. So using trigonometry, we see, because this is 45 degrees, that the x components must be multiplied by root 2 over 2, and the y components as well. Because in a 45-degree angle, the component x is equal in magnitude to the component y, which is why we get the same value here. We see that T1 is positive in the positive x direction, and T2 is in the negative x direction, which is why we have a minus sign. And then it's equal to 0 because there's no other forces acting in y, and x, sorry. Then we get to forces in y. We see that T1 is acting in the positive x direction, which is why this is positive. T2 is also acting in the positive x direction. But then we have this additional gravitational force, mg, which is pulling down, so it's negative. It's equal to 0. This can then be solved, or can be rewritten as an equation in the form of ax is equal to b. So we're going to go over here and rewrite this. In this case, our x is going to be our t1 and our t2s, because that's what we want to solve for. So we're going to set it up as t1, t2. Using this as our x, we can then write our A matrix. So this column is t1, and this column is t2. So we see that it would be root 2 over 2, negative root 2 over 2. And then our t1 in our second equation, again, is root 2 over 2. This time our t2 is positive, root 2 over 2. And we're just going to move this over to this side. So we only have anything that's multiplied by t1 or t2 in our matrix. So that means this t1 is t2. And since we moved our mg to the other side of the equal sign, for our first equation, it's still just equal to 0, but for our second equation, it is equal to mg. So from here, there's a couple different ways you can solve this. The first option is to solve for x using inverses. So you can solve for the inverse of a and then multiply that by b, which in this case, this is our b, to then get our values for t1 and t2. You can also just RREF and then solve the system.